We hear about it all the time, but what actually is quantum physics? I think you'll be surprised. Welcome to our channel, the place where future billionaires come to get inspired. If you've ever heard anything about quantum physics, it's probably been something along these lines. Particles can be in two places at once. Observing them causes them to collapse from being in two places at once to being in one place. If we take a quantum mechanics class, we learn that this happens because particles are waves, and waves can be in multiple places at once. When we observe them, we cause them to collapse by interacting with them, which makes them behave like particles. Actually, those ideas are wrong. Not technically wrong. They're just not really true. Let me explain. A physicist who has studied quantum mechanics for a long time, I'm going to show you what quantum physics really is by showing you what it isn't. In order to understand quantum physics, you have to start with classical physics. Newton was pretty clear that objects exist, and they have properties regardless of whether we observe them or not. This is called realism. If the apple tree over there isn't real, then why do I get wet when I stand under it and it falls on me? Classical physics also says that if you know exactly what an object is doing at one moment, you can predict exactly what it will do at any moment in the future. This is called determinism. Again, if the apple isn't real, then why does it hit me in the head every time I look up there? It's real, and it's determined. This is the basis of classical physics, the idea that things exist and their behavior is determined. Quantum physics turns both of those ideas on their heads. First, let's look at the idea that things exist regardless of whether we observe them. Consider a double-slit experiment. Electrons are fired one at a time at a screen with two slits cut in it. As you might expect, the electrons end up making a pattern on the screen behind the slits that looks like this. We can see that the electrons go through both slits. But what if we put detectors at each slit to see which slit the electrons go through? Wouldn't you expect that if the electrons were real, they would still go through both slits? No matter how clever we are, we can never actually find out which slit the electron went through. It's impossible. And so the detector causes the electron to only go through one slit. The very act of measuring or observing causes the electron to stop behaving as though it's a wave going through two places at once, and instead behave as though it's a particle going through one place at a time. Einstein called this spooky action at a distance. He thought that this meant that the electron must have decided which slit it was going to go through before it was fired from the gun. This is called the measurement problem. If the electron isn't real, then why does it change behavior based on whether we measure it? If it is real, then why don't we see evidence of it in everyday life? The answer to this question is that the electron isn't real until it's measured. Electrons aren't like baseballs. They don't exist in the sense that baseballs exist until we measure them. Then they become real. Second, quantum physics also turns determinism on its head. Once we fire the electron from the gun, we can no longer predict exactly where it will land on the screen. This isn't because we don't know enough about the electron. It's because no matter how much we know about the electron, we could never predict exactly where it will land. It's random. Its randomness is inherent to quantum physics. It's not due to our lack of knowledge. This is called the uncertainty principle. There are other places where we see this randomness in quantum physics. Sometimes it's in the energy of photons. Sometimes it's in the momentum of electrons. And sometimes it's in the position of atoms. The thing that they all have in common is that they are pairs of properties that are related by an equation. If we know one side of the equation, we can't know the other side. This brings us back to the question of what quantum physics is. Well, here's my favorite way to put it. Quantum physics is a set of rules for when we measure nature. That's it. Before we measure nature, we assign probabilities to possible outcomes. After we make a measurement, those probabilities become actual frequencies. For example, if we repeat the double-slit experiment many times, we find that about half the electrons go through the top slit, and about half the electrons go through the bottom slit. Those are the probabilities. Then we measure the electron, and we find that it went through one slit or the other. Those are the frequencies. So quantum physics is a set of rules that tells us how probabilities become frequencies when we make measurements. Okay, big picture stuff, right? Well, maybe not. Here's another way to look at it. You may have heard that quantum physics says that a particle is in two places at once until we measure it. And then we cause it to collapse from being in two places at once to being in one place. If that sounds wrong, it's because it is. But what's interesting is that there's a sense in which it's also right. Suppose we have a particle that's free to move in one dimension. If we measure the particle at one place and find that it's there, then we know that it's there. That seems obvious, right? But what if we want to know more? It's like, what if we want to know where the particle might be later? Unfortunately, we can't. This is because the act of measuring the particle puts information into the particle, and that information changes the particle's behavior. In fact, it forces the particle to change its behavior. In order to see this, let's imagine we're doing the opposite. Instead of measuring the particle and finding that it's in one place, let's assume that we know the particle is going to be in one place. Because of this, we can say that the particle has a wave function that looks like this. We use the notation psi of x bar to mean the wave function of the particle after we learned that it's at position x. After some time, that particle will evolve to a new position, and we can write down the wave function of that new position as psi of x. This looks like this. Psi of x describes everything we know about the particle at position x, the absolute square of its value. That is, psi star of x times psi of x describes where the particle might be in the future. The larger the number, the more likely the particle is to be found there. So the probability of finding the particle at some position x in the future is given by this curve, but that's not what we'd expect. If we knew the particle was at x at the present time, we'd expect it to be at x in the future, wouldn't we? What went wrong? Well, nothing. This is exactly what we'd expect. We just forgot to account for the effect of measuring the particle. In order to account for that, we take the wave function of the particle after we've measured it, psi of x bar, and we square it. The result is this. We can see that the particle spreads out. This spreading is a consequence of having measured the particle. It means that the particle is now less likely to be found at exactly the position we measured it at. Why? Because we put information into the particle when we measured it. This information is recorded in the phase of the wave function. The phase of the wave function is the part that has the weird properties. If we had a second detector that told us the phase of the wave function, then we'd be able to predict the future of the particle perfectly. But since we don't have that second detector, we can only say that the particle will be found at a position that's near to where we measured it. So quantum physics is really just a set of rules that tells us how to interpret the phase of a wave function. There are lots of different ways to do this. We typically use the Born rule, which says that the phase doesn't do anything. But if we used a different rule, we'd have a different theory. Maybe you've heard that we can exploit this to create free energy or teleport faster than light, or do all kinds of crazy things. Unfortunately, that's just not true. This is because the phase of the wave function only carries information about the particle itself. It doesn't carry information about the apparatus that's being used to measure the particle. So the phase of the wave function can't be used to do anything clever. The bottom line is that quantum physics is really not all that complicated. It's just a set of rules that tells us how to interpret the phase of a wave function. But it's also not easy. It's hard to do calculations with wave functions. And in fact, most physicists don't do them by hand. They use computers. Quantum physics is really just a set of rules that tells us how to make predictions about nature. And in that sense, it's no more or less real than classical physics. If reality feels broken now, then you're ready for more. Hit like and subscribe for deeper dives into the quantum world. Thanks for watching.